Hi, everyone. So welcome to this evening's live stream. So what I'm going to do this evening is cover all of waves for both physics 112 and 102. So this is both the calc and the non-calc stuff. I'm going to do the common stuff first and then leave the stuff that's only for physics 102 after that. So just to show you here, the first 7 questions, they are common to both the calc and non-calc students. And then I have this big danger sign there, okay? And questions 8 and 9 will be just for physics 102, that is for the calc students, okay? When I publish this, I'll put timestamps on it so that if you're the physics 102 students and you want to go directly to that stuff, you can do that. All right, well, let's start. Wave phenomena. What is it? It's basically where you have coupled oscillators making up a medium. A medium is just a material that can sustain a wave. Like Jello is a good example of this, or water, or string, or many examples. Even empty space can sustain waves. As electromagnetic waves. Okay, so any material where every point in it can be treated like an oscillator that then influences its neighboring oscillator will give rise to a wave. Okay, now the first equation that we looked at was the equation that describes the velocity at which waves travel. All waves in a particular medium travel at the same speed, but they might have different wavelengths and corresponding to that different frequencies. Okay, so that's what my first example is all about. A microwave oven produces microwaves of a frequency of 2.45 gigahertz. What's the corresponding wavelength? Okay, and this is actually a number that I got offline, so that's a very real number, 2.45 gigahertz. There's your frequency. That's the F right here. Okay, and I'm asking you to find lambda, and you say, well, wait a minute, don't I need V? And the answer is yes, but V is the velocity for the speed of light. Now, why the speed of light? Because all waves that form part of the electromagnetic spectrum travel at the speed of light, and those are like radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. They all travel at the same speed, and that speed is, well, let me do it down here. V is 3.0 times 10 to the 8 meters per second. Okay, so that's the speed of light. I would give you that on a test. Okay, although it's not that hard a number to remember. So there's your V. Your F, which I gave you as the frequency, is 2.5 gigahertz. Okay, now the hertz is per second. But that's not the problem. The giga is the problem because that's not MKS. Giga, this you do have to know, is 10 to the 9. So 10 to the exponent 9 per second, like that. Okay, and so this part here is the hertz. And then just substituting this into the equation, we have V is equal to lambda multiplied by F, which is this. Okay, or lambda, just dividing both sides, is equal to this. We put it in brackets, divided by this. Okay, so all I did was divide both sides by the frequency. And what's that number going to be? Should be a few centimeters. Doesn't like a few things here. Okay, there we go. So there it is, to 3 significant figures. Okay, now MKS, that's meters. Okay, so 0.122 meters, like that. All right, now in centimeters, that's going to be 12.2 centimeters. All right, so this is a real number. That means that the microwaves in your microwave oven actually have a wavelength of about that much. Okay, about 12 centimeters. Okay, so there you go. All right, well, let's continue. The next thing that we studied was what determines the speed of waves in a particular medium. And now that's going to be dependent on the medium. So I really only gave you this for one particular situation, and that was for a string. Okay, so if you have a string and it has a certain linear mass density and has a certain tension on it, waves will propagate in that material at a certain speed. Okay, and so here's a typical question. Excuse me, 5 meters of a wire, some kind of a metal string, okay, so of a wire, has a mass of 1.25 kilograms. Okay, what tension is required to obtain waves of speed 350 meters per second? Okay, so the first piece of information here, 5 meters has a mass of 1.25 kilograms. That gives you the linear mass density. Because this is a string, it doesn't make sense to talk about its density as a volume density, like mass divided by volume, but it does make sense to talk about it mass per unit length. And so that's what this quantity is here, mu. Okay, so let's calculate that quantity over here. So mu is equal to, for m, it's going to be 1.25 kilograms. It's already an MKS for you, okay? And the distance is 5 meters, okay? Again, already an MKS. And so this works out to 0.25 kilograms per meter. Okay, it's a fairly hefty string. Okay, it's a heavy string. Okay, now the next thing is this equation right here. And that is particular for different materials, like you might say, what determines the speed of sound in air? And it turns out to be the bulk modulus of air divided by the density of air. Okay, so they all have or square root of that. Okay, so they all have similar forms, but I only expect you to know one of them, and that is for the speed of waves on a string, and that's equal to the square root of the tension in the string divided by the linear mass density. Okay, and we actually have a lab where we'll make use of that equation. All right, so let's calculate that. Well, I actually tell you what V is. So let me put this down here. I tell you what V is, so you know V, and you know mu because we just calculated that, so we want to find T. So before I plug in, it'd probably be best if I just go ahead and rearrange this to isolate T, the tension. So I'm going to square both sides. Okay, so there it is squared. Of course, when you square, the square root goes away, but on this side you get a V squared. And then your linear density, multiply both sides by, you can multiply, sorry, we want tension, I apologize. Isolate the tension, multiply both sides by the linear mass density, so we'll have linear mass density multiplied by V squared like that. Okay. And that's going to equal 0.25, okay, because that's our linear mass density in MKS units. And V, that is 350 meters per second, okay, and that's going to be squared, and so that's going to turn out to be a tension of, let me calculate that for you, 30,625 newtons. Or if we were to round that off, 30.6 kilonewtons. Okay, this is a pretty big number, but that's because I've got a very thick string there. Okay, like a linear mass density of 0.25 kilograms per meter. That's like 250 grams per meter. Okay, so like half a pound per meter. So this is a really thick string. It's not like a guitar string. Okay, and so you're going to need quite a bit of tension in that to get 350 meters per second waves. All right, so well, there we go. Okay, so that solves this problem. All right, now the next thing we did was first we talked about waves just on a string, okay, or on any medium which is not bounded, which is not tied down on both ends. And then I said, well, in reality, you usually have the medium which is bounded somehow. Like if it were Jello, the Jello would have some boundary. Okay, if it's a string, which is what we're going to consider in a second, the string is tied down at 2 points. Okay, take a look at a guitar. You have a bridge at the head and then another one on the body, and the string just between those 2 points gets to vibrate, not the string up beyond those 2 points. Okay, so in one way or another, the material that unless it's infinite and nothing's really infinite, and I don't want to describe why empty space is not even infinite. But like any material is bounded, and so all waves within that material are actually what are known as standing waves. Okay, and so standing waves, what that means is that you can't just get any old frequency in there, and you can't get any old wavelength. The wavelength has to be commensurate with the boundaries. Okay, so if you have boundaries like this, you can have half a wavelength in there, you can have a full wavelength in there. You could only have these certain integer multiples of wavelengths in there. Okay, and corresponding to those integer multiples of wavelengths, you have integer multiples of frequencies. Okay, and so how does that work? Well, let's take a look at our third problem here. So the question is, how much of this string, now I didn't solve this problem yet, so I'm not sure how long it's going to be, but we'll find out. How much of this string do we need, do we have to tie down so that the lowest possible frequency is 514 hertz, okay? And what is the next possible note, okay? So, so there's a lowest frequency. When you've got a string which is tied down, and you pluck it, you'll get a lowest frequency, the fundamental frequency, okay, and then you'll get higher frequencies. The higher frequencies are integer multiples of the lower frequency, okay, and the lowest frequency, which I called F naught there, is given by the velocity of waves in that material divided by 2L. Notice here I put a capital L because up here I used the little l for the length, like certain mass per unit length. Here, that capital L, that's how much is tied down. I just wanted to distinguish the two lengths in there, okay? So let me do that problem for you. Okay, whoops, wrong screen. Okay, so over here, the fundamental frequency, I told you I want it to be 514. The velocity, I told you, was 350 meters per second. Okay, see it right there, 350 meters per second. So there's the velocity. Okay, substituting for that, divided by 2 times L, and we're trying to solve for L. Okay, and so well, I mean, I guess I can do this in 2 steps. All right, 514 is equal to 175 divided by L. So I just took the 350 and divided by 2. And then what's L going to equal? Well, L will equal, let's do this, 514 divided by 175, like that. Okay, so what did I do? I multiplied both sides by L and then divided both sides by 514, and that will equal, what will that equal? Let me get that for you. So there it is, to more digits than you need, but rounding it off to 3, 2.94, and L is a length, so it's meters, like that. Okay, so you'd have to tie down approximately 3 meters in order to get a frequency of 514 hertz. Okay, so well, that's that problem. Okay, so there you go. Let me just take a little sip of tea. Sorry about that. My house is very dry, so it gets hard to talk when your throat is dry. Okay, anyhow, so there we go. That's the story with standing waves. What's the next one? Well, the next one is beats. And beats, the formulas are pretty easy, but the concept's a little bit tricky. So I've got, we'll do the problem, and then I've got a little demonstration for you, okay, to show you what beats are, okay? So first of all, when does beating occur? It occurs when you've got 2 notes which are of close frequency, but not exactly the same frequency, okay? And I say notes because usually we hear it in sound, but beating will happen in any medium. So it will even happen with waves on a string or whatever, okay? But as far as we're concerned, like, when do we hear it as humans? It's usually with musical instruments, okay? In fact, how you use beating to tune musical instruments. Okay, so we have 2 notes. We're going to play 2 notes together. One note is 455 hertz, and the other note is 459 hertz. And the question is, what do you hear? Okay, and so what you hear is this. You'll hear a resultant note, which is actually the average of the two, and you will hear a beat, which is the difference between the two. Okay, so let's calculate those, and then I'll show you how they work. All right, so let me substitute. All right, so there's the two frequencies, and the average of that is going to equal. Oh, I didn't need a calculator for that. That was silly. 457 hertz. Okay, so there's the average of the two frequencies. You would hear a note of that frequency. Okay, so you wouldn't hear a 455 note and a 459 note separately. It would sound like the two notes mixed together, and they would give you a note of 457 hertz. So like a frequency right in the middle. Okay, now what would you hear in addition to that? You wouldn't just hear that note like as a steady note. You would hear that note, but it would go loud, soft, loud, soft, loud, soft. And the rate at which the loud soft occurs, that frequency is actually the difference between those two. Okay, and so that's going to equal the following. Notice those lines there. Maybe I better show you how this works. Those lines there are actually absolute values. Okay, so it doesn't matter which one's bigger than the other. Okay, so whoops. So technically, if you did the subtraction, you would get -4, but the absolute values, so those straight lines there are absolute values. Just say, no, I don't care which one's bigger than the other. It's just whatever the difference is in positive, whatever the positive difference is. So it's like 9 minus 5, which is 4 hertz. Okay, so you would hear the thing going loud and soft 4 times per second. Okay, again, you would hear a note of that frequency, 457 hertz, but that note would go loud and soft 4 times a second because the beat frequency is 4 hertz. Okay, now never mind what you would see on an oscilloscope just yet. Okay, let me switch to another screen because I want to show you what's going on here. Okay, so this website that you're looking at right now is called Desmos.com, and it's a really nice site because it allows you to actually plot functions. Okay, now what you're seeing there is actually the plot of cosine 455. Now, first I better say something. Technically, that's not the 455 hertz. Really, there should be a 2 pi in there, but that's okay. We won't worry about that. This is just for purposes of demonstration. So if you're wondering like why I've dropped the 2 pi, it really doesn't matter for the demonstration. Now, when you plot this function, okay, it's a cosine function, and you look and you see this solid thick red line, and you go, what's going on there? Like, why don't I see the usual sinusoidal wave? And that's because the crests and the troughs are very, very close together. So let me zoom in for a second. Here, let's zoom in, whoops, zoom in, let's zoom in right there. And now you're starting to see the crests. Okay, so you see the crest there. There is a crest right there. Then it goes way down to a trough, and there is another crest there. There's another crest there. There's another crest there. There's another crest there. So the distance between those two crests, that's a lambda, for instance. Okay. Now, of course, when you zoom out, they kind of just like they get so close together that it looks like one big solid, you know, a bar there like that. Okay, this would be some note, something would be a steady note. It'd be like like a constant steady note, not going louder, not going softer. Okay, now that's 455. If I switch that to 459, as you might expect, not much difference. Okay, like you can't see a difference. All right, so 455 plus 450, sorry, 455 will give you that. 459 gives you that, but they're slightly different. Okay, they're slightly different, although you can't see it. If we add the two together, guess what you see? So let's go back to 455 here, plus cosine of 459. Oh, and this is x because Desmos works with x instead of t, but you can think of the x variable there as your time. Okay, and take a look at what you're seeing now. You're not seeing a solid red bar, which would be like a solid sound, okay, like a solid note. What you're seeing is loud, loud, soft, loud, soft, loud, soft, loud, soft, like that. Okay, and well, there you go. Those are the beats. So this one blob right there, that's a beat. This would be its neighboring beat, and then a neighboring beat, and so on. Okay. Now, what would you hear? You would hear Okay, so you would hear a particular frequency, but that frequency itself would go loud, soft, like that. Okay, and if any of you play guitar or violin or viola or any of the stringed instruments, you know that you make use of this phenomenon to tune it, because what you want to do is eliminate the beats, because when the frequency is exactly the same, so this is 455, that's 459, but what if they're both 455? You're back to your solid note. Okay, so when the beats disappear, the the notes are, the two strings are at the playing the same note. Okay, so there you go. All right, and back to that, you can see the beats again. Okay, last thing, one of the questions was, well, what would you see on the oscilloscope? The oscilloscope can actually tell that neighboring beats are not the same. You can't hear that this beat and that beat are slightly different, but they are. Okay, so as far as humans are concerned, this beat and its neighboring beat are the same. But as far as an oscilloscope is concerned, let's zoom into the middle right here, right where it goes quiet. Okay, you will notice it's slightly not symmetrical there. Okay, see how it kind of does a small little crest there and then a bigger crest there. Your ear cannot hear the difference between the two neighboring beats, but an oscilloscope, if you watched it on the screen, and we will play with an oscilloscope in the lab. Okay, basically what an oscilloscope does is it shows you the waveform. Okay, so what the oscilloscope will do is it'll actually show you that waveform, and you could tell that one beat and its neighboring beat are not exactly the same. Okay, something that an instrument can see, but not the human ear. Okay, so there we go. There's the story with beats. Okay, so there's question number 4. All right, see if there's anyone in the chat, if there's anyone that has questions. In the meantime, I've got to drink a little bit more tea. Okay, so it seems that some people say I made a mistake on question number 3. Let's go back to question number 3. What did I do wrong? When I divided those two, what did I do wrong? I probably did it wrong. No, I'm still getting. I'm not sure why you guys got 0.34 here. So, let me see here. We have this. That's this. And here, I could do this a different way. Let me just see here. So let me multiply both sides by 2L, so that I would have this. Okay, like that. All right. And then I can multiply L. I can bring the 2 times the 514, so that'd be 1028, like that, is equal to 350. And then L is going to equal, I think I did it wrong. Haha, you guys were right. Okay, so I don't know what I did wrong there. Yeah, I don't know. I don't know what I did wrong, but I thank you for showing me that. You're right. So there's the answer. Okay, so that corrects question number 3. Okay, so thank you for pointing that out. As I said, I do these things on the fly. On purpose. Okay, and the second part of question 3, you're right. I did forget the second part of question 3. The second part of question 3 is it's pretty easy. If this is the lowest note here, like that, F naught is equal to 514 hertz, like this. Okay, then the next one would be F1, and that would be, sorry, it would be F2. you know what? I should have probably called this one F1. Let's call that F1. F2. And the reason I want to call it that is because this would be like for n is equal to 2, 3, 4, 5, like that. Okay. It really doesn't matter what you call the fundamental, but I guess we could still call it F0. That's what I call it. Let's stick with that. I hope that's not confusing to you. But there's the F0. But here, you know, for the next one, it'd be F2, and it'd be 2 times the fundamental. So it's going to be 2 times the fundamental for 514 hertz. So the next one would be 1028 hertz. And then if I want to ask for the third, that would have been 3 times 514 hertz, like that. And that is going to equal 1542 hertz, and so on. Okay, so basically there's the fundamental, twice that, 3 times that, 4 times that, and so on. Okay, and so there was another question, which is on the oscilloscope. So humans would hear this. Okay, the oscilloscope would actually see this. Okay, so I didn't ask that question because I didn't want to overly confuse it, but the oscilloscope, but I did do this in the notes, so I'll mention now. The oscilloscope, okay, what it would actually see is this frequency here, half of that. Okay, so you don't hear this, but this is what the oscilloscope, if you ask the oscilloscope what's the beat frequency, the oscilloscope would actually say this, whereas you would hear that. And you go, well, why is that? Why would the oscilloscope give you half of that? Now I can show you why now on the browser, this other screen right here. Okay, so if you take a look here, let me zoom out. Okay, take a look here. This beat and that beat are different. Okay, but this beat and this one over here, the one like 2 over, so this one and that one over there are identical. Okay, you can't see that, but the oscilloscope can. And so the oscilloscope says, well, it doesn't, the beat doesn't repeat here to there to there to there. The beat repeats from there to there, and then the next one over. In other words, it sees, the oscilloscope sees the beat every 2 over. Now, if you go twice as much in time, that's half the frequency, and that's why the oscilloscope sees it at half the frequency. Okay, so I mean, I did mention this in the notes, but I didn't want to cause too much confusion as to why the two are different between one another. Again, this is the one you were going to hear because you can't tell that the 2 beats aren't identical, but because the oscilloscope can, it actually has to look over 2 beats before it sees a repetition, and so it would actually measure twice that. Okay, so so there we go. All right, let me see if there's any other comments. Yeah, I think I explained the difference between 4 and 2. Okay, and 175 should be divided by 514. I think that was in response to my mistake that I made before, but I'm pretty sure this is correct right now. Okay, so well, thank you very much for noticing all that. Okay, so let me see if there aren't any more questions, I can move on. Okay, probably went just a bit too fast there and made some mistakes. All right, so okay, let's go on. Okay, and I'll look back if there are any other questions. I'll look back and go back. Okay, so question number 5 is just a description of some phenomena. Okay, that waves exhibit. Okay, and so you should know what these are. Just a verbal description. All right, and so what are those phenomena? Well, one of them is reflection. And that's pretty easy. If you've got a ray, and remember the ray is the line that just traces out the direction in which the wave fronts move. If you've got a ray and you trace it, when it reflects, the incident angle is equal to the reflected angle. That's it. There's nothing very deep about reflection. We didn't even do any problems about it. The only thing is that you just need to know that, okay, so that the incident angle is equal to the reflected angle. Okay, so what's refraction? Well, refraction occurs when you have 2 media which are joined together. Okay, and the 2 media could be like water and oil, which I'll do in a second, example of that, or water and air. So water, not water waves, but light waves in water. Okay, so light will travel through water, and light will travel through air. Like if you've got a laser beam, light will travel through it. But light travels different at a different speed in water compared to air. Okay, so by the way, that speed that I gave you up above here, this speed right here, and I said that was the speed of light. That is the speed of light in a vacuum. Okay, so speed of light in a vacuum. In other words, an empty space, okay? And that's the fastest light is going to go. Now, if you've got light in some other material traveling through, say, water, it travels a little bit slower, okay? And so, when light travels from, say, water to air, the speed changes. And when that speed changes, it'll actually bend. The rays will bend, okay? And so that's what refraction is all about. It's basically the bending of rays when a wave travels from one material to another material, okay? And total internal reflection, okay, is actually what happens in refraction when you go from a material of higher N to a material of lower N at a very big angle to the normal, okay? And I should draw that, and I'll draw that in just a second. But right now, let's just it's part of refraction, so it's the extremes of refraction. If the wave is traveling from a material of a bigger index of refraction to lower, so it's got to go from bigger to lower index of refraction, and the angle is big, the angle to the normal is big, or beyond a certain critical limit, then you get total internal reflection. The refraction goes away. I said refraction there. That should be reflection. Total internal reflection. There we go. The refraction will go away, and it'll switch over to the refraction will go away, and it'll switch over to reflection. Okay, and let me draw that for you. Okay, so let me switch to a whiteboard here. Whoops, I need a new whiteboard. Oh, right here. Okay, there we go. So if we have an interface here between water and air, so like here, like this is, let's say this is water down here. All right. Let me see. Can you see that? You can. Good. Okay, so you got water down here, and you've got air up here, like that. And let me just use red for the construction line. So this is the normal, like this. And I don't know. Let's use yellow for a beam. So here's a beam of light like this, and it's traveling. This is the bigger end, so that's bigger, big here. This is big index of refraction, and this is small up here. The N is for index of refraction. That's small, like that. Okay. When you go from bigger to smaller, you actually bend away from the normal. Whoops, that's too steep. There we go, like that. Okay, so I don't know, suppose that this angle in here, that's not easy to see. Let's do, okay, suppose that angle in there were like 40 degrees. Okay, this angle here, and I'm just guessing at these numbers, okay, but about right, that would be like 60 degrees. Okay, in other words, it's bigger here than it is there. Okay, now when does this refraction turn over to reflection? Well, imagine that I keep making this angle bigger, so 40, then I go 45, and so on. Eventually, let me clean this up a bit. Eventually, I get to an angle like this. Well, let's do it in yellow. I get to an angle like this. And at this point, the angle over here actually reaches 90 degrees. Well, you can't refract more than that, so this becomes the critical angle. Okay, theta C, okay, for a critical angle. If you go past that in the water, well, then you're not going to, let me clean that up actually. Okay, so this one, suppose, let me do that in a darker, this next ray like that, that's steeper. Well, you can't refract more than 90 degrees in air, so you know what? You reflect like that. Okay, so the orange line that you see there, this line right here, reflecting there, it's past the critical angle. So if this is the critical angle, and you're at an angle bigger than the critical angle, so you're at an angle bigger than the critical angle, you don't get refraction anymore, you get reflection. Okay, so that's the story with total internal reflection. Okay, it's the extremes of refraction. Okay, all right, so let me see if there's any questions so far. Nope. All right, so diffraction, when does that happen? So diffraction, let me draw that too. Oops, wrong. There we go. So diffraction, when does that happen? When you have like a border like this. So here's a barrier like this. And you've got these wave fronts like this. So wave front, wave front. The blue lines there, you can consider them to be crests. Okay. Well, you know, they'll get clipped by that border there like that. And you might think maybe this is what they do. You know, they just get clipped and then they continue, but not quite. They'll bend. They bend around the corner. So they'll bend like that. They'll bend like that. They'll bend like that. They'll bend like that. Okay. And so this piece in here, like that piece right in there, encircled in the red, that's the diffraction. Okay. And diffraction, another way to think about it, is that you don't get sharp corners. Waves do not produce sharp corners. Okay, when they go across a barrier or past a barrier like that, where they get clipped, they don't form a sharp shadow. They'll make actually a smeared out shadow. And the smearing part of it, that's the diffraction part. Okay, and then finally there's interference. For interference, you have to have two or more sources. Okay, and each source is producing a series of crests and troughs. And whenever you're in a region of space and a crest coming from one wave meets a crest coming from the, a crest from one source meets a crest from the other source, the two crests, they kind of help one another and they make a bigger crest. Okay. And the same thing when a trough from one source meets a trough from the other source, both troughs help one another and they make an extra deep trough. Okay. Or you can get a crest from one source, meaning a trough from the other source, and they kind of annihilate one another. Okay, and what that does is it creates regions where there's constructive interference. That means extra big crests or extra big troughs. And then there are other regions of space which lead to destructive interference. And destructive interference are regions where basically there's no wave. Okay, and so that's what interference is. All right, so let's do some problems with that. Okay, so the first one is, whoops, that's clipped off. All right. So the index of refraction of water is 1.33 and of oil is 1.47, clear oil. Okay. Oil floats on water, obviously. And if we pass a ray from the oil to the water at an angle of 45 degrees to the normal in the oil. Okay. So in the oil, the angle, the ray is making a 45-degree angle. What's the angle in the water? Okay. And I should probably draw that. All right. So what's that going to look like? That will look like, here's the interface, oil's on top, water underneath, like that. And we've got a ray. Let's make the ray, let's do orange. It shows up a little bit better like this. Okay. And remember, this is the bigger N. So this is big up here. Big N is big up here, and N is small down here. In the small region, it bends away from the normal. The normal, let's do the normal in blue, is kind of like, you know, if it impinges there, that's the normal there like that. Bending away from the normal means that this angle here, like it doesn't go straight through like that. Okay, that would be like no change at all. It bends away from the normal means that it's going to bend at a more steep angle like that. Okay, and I'd say that this angle over here is 45 degrees. And I ask, what's this angle down here? Okay, so let's switch back. All right, so there's the formula. This is known as Snell's law. Okay, there's the formula. And I just used the generic N1 and N2 for the the indices there. But N1, we can say that's like the water. So the index of refraction in water is 1.33. Okay, the angle in the water, let me get a theta here. The angle in the water, call it theta 1. That's unknown. That's what I ask you to calculate, okay? What angle does it make to the normal in the water? Okay, so that's the angle in the water. Angle to the normal, okay? N2, that's going to be for the oil, and the index of refraction there is 1.47. All right. Almost clipped off, but it isn't. Okay, so that's oil. And the angle for the oil, the angle to the normal in the oil is, I said, 45 degrees. Okay, so the rest of it is just a matter of plugging in. So for N1 here, 1.33. Sine theta 1, we don't know theta 1. Okay, and then over here for N2, we have 1.47. And then sine of, and the angle in the oil is 45 degrees, like that. And so equals, on this side you will get malformed expression. There we go. All right. Let me grab a few more decimals here, like that. Okay. And then divide both sides by 1.33. So I get that sine of theta 1 is equal to that. Okay, so what did I do? I just took 1.33 and divided by both sides. Okay, and now what? Well, you're trying to solve for that theta 1, so you have to take the inverse tangent of both sides. And the inverse tangent basically unfolds the sine there. No, not inverse tangent, inverse sine. The inverse sine like undoes that sine, but then over here you get sine inverse of that value right there. Okay, so make sure you know how to do inverse sines. Like on some calculators you do it this way. Some calculators you have to press like the second key and then the sine. But one way or another, you'll know that it's the inverse sine. Okay, and you just have to figure out how to do that on your particular calculator. And what's that going to equal? Also malformed expression. How come? Oh, I know why. All right. And that's going to give me a theta 1 of 51.4 degrees. 51.4 degrees. Okay, so there we go. 51.4 degrees. Okay, so if I switch back here to the whiteboard, that question mark there, that is 51.4 degrees. And is that correct? Well, we expected, I don't know if the exact number is correct, but we expected this number to be bigger than the 45 degrees, okay? And it is, okay? So again, the smaller n is, the bigger the angle, all right? Great, now what? Well, the other question I asked was, what's the critical angle? And you can see that at 45 degrees, you're not at the critical angle yet. So you're going to have to be at an angle bigger than 45 degrees. I don't know what that angle is going to be, but let me do that. Let's say I'm going to do this ray in red. At some angle here, which we have yet to calculate, okay, at some angle there. So this is bigger than 45 degrees now. Okay, I don't know what it is yet, but that's what we're trying to find. That's what our theta c is going to be. At some angle bigger than 45 degrees, this ray is going to, it's going to be more than 51. In fact, it's going to reach 90 degrees like that. Okay, so that'll actually expand up to 90 degrees like that. Okay, now in the smaller n, that's where we put the 90 degrees. Okay, for the critical angle in the region of smaller n, that's where the 90 degrees is, and then we find the theta c, okay, in the region of bigger n. All right, so over here the other question was, what is the critical angle, all right, at which total internal reflection begins? Okay, so the formula is still the same formula. It's still this formula here. Copy paste. Okay, it's still this formula here, but now what? Well, N1, that's your air. Okay, that's sorry, the water, and the water is the smaller n. Okay, in the region of smaller n, that's where the 90 degrees occurs. So N1, N for water, okay, is 1.33. Sine theta 1, that's your 90 degrees there, like that. Okay, so again, if you say, well, where should I put for the critical angle, where should I put the 90 degrees? With the smaller n. Okay, then on the other side you have equals N2, and N2 was index of refraction for oil, 1.47, and the angle in the region of bigger N, that's your theta C, that's your critical angle. Okay, so so you see how I put that together? All right, again, smaller n, that's where the 90 degree is. Bigger n, that's where the theta C is. Okay, so let's solve this. All right, so let's divide both sides by 1.47. Sine of 90 degrees, by the way, 1. Okay, so this is just going to equal the following. All right, sine of 90 degrees is 1. Okay, and so 1.33, it's the inverse sine of 1.33 divided by 1.47. Okay, and that gives me an angle of 64.8 degrees. Okay, that's what your theta C is going to be. All right. Oh, I lost my C. There we go. That's what your theta C is going to be, 68 degrees, like that. If you wonder what I did there, well, maybe I should just go a bit slower. So I just did 1.33 divided by 1.47. Okay, that's going to equal sine theta C. And then I just did the inverse sine of both sides. And the inverse sine and the sine, they kind of cancel one another out. So that isolates the theta C. So I just did the inverse sine of 1.33 divided by 1.47, and that gives me 64.8 degrees. Okay, so back over here. That diagram is getting a bit messy, but this theta C right here, that angle in there, like that. That angle we just found to be 64.8. Okay, so when you get to 64.8, you know what? Let me clean up a bit here. Let me clean up a lot, actually. Okay, so when you get to this angle of 64.8, that's it. You can't refract any more than that because you're at 90 degrees. Okay, you're at 90 degrees in the water. What if you try to go further than that? Okay, I'm running out of colors here. Let me just do it in black. Suppose I send in another ray here, and I send it in at, I don't know, 70 degrees. So say that's 70 degrees. What happens? It does not penetrate the water at all. It just bounces back into the oil. Okay, so that's it. You know, at past 64.8 degrees, at angles bigger than 64.8 degrees, the ray will simply not get into the water at all. It'll just bounce right back into the oil. And you know what we can say is, if this is coming in at 70 degrees here like that, then it actually reflects at 70 degrees. Okay, because now we're talking reflection. All right. So there's the story with refraction. Let's take a look in the chat. All right, no more no questions. Okay, so let's go on to our last question for the non-calc students. Okay, so I shouldn't say the non-calc students. This is the common stuff for both classes. Okay, so beyond this, that's where the calculus starts. Okay, so the next question is question of interference. Okay, and you'll actually do this in the lab. One of the labs is we'll have water waves on a water tank, and we're going to use like these wax barriers, and we'll actually make like these barriers where a double slit where the waves will pass through the double slits and then interfere with one another. I'll draw that picture in a second. Okay, so Let's read the question first. Water waves with a wavelength of 1.5 centimeters passes through two slits a distance of 4.5 centimeters apart. Okay, at what angle does the first dark region? Now, when I say dark, I should say quiet or non-wave region. Okay, at what where does that occur? And at what angle does the first light or bright or high wave region? Okay, when we're talking about water, it doesn't quite sound right to say dark and light. With light, visible light, you can actually do this with a laser. Okay, and if I can find a diffraction grating for my students in the lab, I'll actually demonstrate it for you, okay? Because you can do it with a laser beam, and you can use these things called a diffraction grating or interference grating. It's just like many, it's actually not just two slits, but it's many slits which are close to one another, and the results are quite spectacular, okay? And you get these light, dark, light, dark, light, dark regions side by side, okay? But with water, what do you mean by a dark region? It just means a region of quiet where there isn't much wave, and by a light region, it would be a region where there's like the waves are pretty big, okay? Let me draw a picture of this. There's the formula for it, but let me draw a picture of this first, okay? So, okay, so first let me draw a double slit. So this is a barrier here like this. And like in the lab, this will actually be wax. Okay, and then we'll have a hole there like that. And then there's another barrier like this. Okay. And another barrier like that. Okay. So this is a hole right there. And this is another hole right there. Okay. Now, the distance between these two, I'll just draw it for a second and then I'll rub it off because I don't want to make my diagram too messy here. That distance between the two holes, and you might say, well, where do I measure from? It doesn't matter. Say from the center here, like that's maybe the center, okay? So the distance there is like 4.5 centimeters, okay? That's in our particular problem, okay? So the distance between the two holes is 4.5 centimeters, okay? Now, we've got waves coming in. And here's a wave front, here's another wave front, here's another wave front like that. And the distance between any two of these, whoops, not red, let's do it in red. The distance between any two of these, like that. Let's see how, oh, I'm sorry, guys. I apologize. I didn't switch, let me do that again. Let me do that again. I apologize. Okay, it's okay. Okay, so let me see. Can you see this? You can. All right. So I didn't switch screens. Okay, so what you're seeing here is the hashed in area here. This is a barrier. Okay, and there's another barrier there like that, and there's another barrier like that. And in the lab, you'll do this with a water tank. And so this is all water here, and these are like wax tablets there like that, 3 wax tablets. And there's a hole here like this. So there's a hole there like that, and there's another hole like that. Okay, let me see. Can you see that? Yeah, you can. Okay. I sorry guys. Okay, so the distance between those two holes here, like this, the distance between those two holes is from the middle to the middle is 4.5 centimeters. Okay, for this particular problem. All right, and we have waves coming in. So these are the wave fronts like this. So those are like the blue lines are like the tops of the crests. So you're looking down on water waves, and the distance between any two of them, I tell you that the distance between those two is 1.5 centimeters like this. Okay. When the waves get to the two holes, what happens? Well, what happens is, so here's like a wave inside there. There's maybe another wavelet inside. There's another one. There's another one. There's another one. There's another one. When they get outside, they'll start to diffract, right? Because they'll turn into circles like this. See if I can not make a mess of this. So these, the ones that I just showed you there, they're all coming from that hole there like that. Okay. Okay. Now let me do the same, but coming out of this hole like this. Whoops, let's do it in, well, let's do it in blue. I was going to do it in red, but it might get too confusing. Oh, there we go. There's another one. And there's another. Not too bad. Okay, not too bad, all right? Now, let's take a look here. What's happening right there? What's happening right there? What's happening right there? Those regions are regions where crests are meeting crests, right? Because the blue lines are crests, and you can see that there's a cross between two blue lines, so those are all crests meeting crests. So this region right here in the very middle, you could call it bright. I don't know what you would call it for waves, but this is a region of like where the water waves are very big. Okay, now what happens between, let's do it in a different color, let's pick green. What happens between two crests? So this is a crest here from one, but this region right here, that region right there is a crest meeting a trough. The crest from the lower hole meets a trough from the upper hole. Okay, same thing right here. Okay, notice that this is between that one and that one. So what's between two crests is a trough. So it's a trough from one, but it's meeting a crest from the other one. And so that's another one. So all along this region here like that, that's what we call dark. Or basically just like not, crests and troughs are annihilating one another. Okay, so that's what's going on. And there's a formula that tells you the angles at which these things occur. The very middle one always occurs, this middle one always occurs at 0 degrees. This one occurs at some angle, and we're going to calculate that in a minute at some angle. By the way, past that, you see here, what's going on there? That's another crest meets another crest. Okay, and I didn't extend these, but guess what? There's another angle here, and that's another bright. Okay, it's terrible writing. There we go. That's another bright in there. So what do you get? You get bright, dark, bright, dark, bright, dark. So you get these stripes of bright, dark like that, and you say, okay, at what angle do they occur at? And there's the formula. Okay, that's the formula that'll tell you at which they occur. The dark occur at angles where n is equal to a half, 3 halves, 5 halves, and so on. Okay, those are the dark. And the light occur at n is equal to 1, 2, 3, 4. I guess I should say 0, 2, because 0 is always there. Okay, but it's not the first one, it's the middle one. So, all those ones, those are all the light. Okay, so a little bit of a repeat of the theory, but there we go. Okay, so let's go through the problem. Water waves with a wavelength of 1.5 centimeters. What's that 1.5 centimeters? That's your lambda. Okay, so lambda I said was 1.5 centimeters. Okay, by the way, in this problem, you really don't have to convert all to meters, because if you work in centimeters with d and centimeters with lambda, it'll work out. Okay, so let's just work with centimeters for this problem. Okay, so d, what's that? That's the distance between the two holes, and I said that that's 4.5 centimeters right there. Okay, and n, well, that depends. What do you want? The first question is, at what angle does the first dark region occur? Okay, so dark occurs at a half, 2, 3 halves, 5 halves, and so on. The first dark region occurs at a half. So I'm asking for the first dark region. That's n is equal to a half there, like this. Okay. And what do we want to find? Well, it asks what angle, so we want to find theta. Okay, so take this formula, substitute in. For d, we've got 4.5. Theta, that's what we're trying to solve for. N, we just said, was a half. And lambda is 1.5. Okay, so what's this work out to? Well, sine theta is going to equal, divide both sides by 4.5, right? Whoops. Okay, so we've got this divided by that. All right, and what's that going to equal? All right, like that. And then take the inverse sine of both sides. And that'll give you a theta of 9.59 degrees. Okay, so for the first dark region. All right. See if there's any questions so far. Oh, so far so good. All right. Now what? Now oh, my phone. Now the first light region. So the first light region occurs at n is equal to 1. So we'll take this equation right here. Do the same thing again. In fact, you know what? We could just copy and paste this right there, because that is this equation here. All right. Oh, didn't work. Copy, paste. Okay. But now for the first light region, instead of a half there, we want 1. Okay. And so now we're going to divide both sides by 4.5. We're going to have 1.5 divided by 4.5. All right, that's what sine theta is equal to. Take the inverse sine and you will get inverse sine of 19.5 degrees. Okay, 19.5 degrees. All right. So, whoops. There we go, 19.5 degrees. So the first dark region is occurring at 9.59, and the first bright region is occurring, at 19.5 degrees. Okay, so there you go. There's the story with interference. Okay, and back to that diagram very quickly, just to show you what's going on here. Okay, so this angle right here, it's getting a bit messy. Let me see if I can clean up a bit. Well, okay, that's good enough. Okay, so there was like that. So green. All right. So in the very middle, right down the very middle, that's 0 degrees. That also corresponds to n equals 0. Okay, that's always true. Right down the very middle at 0 degrees, you're going to have a bright region. Okay, the first dark region occurs here. We found that to be, what was it again? 9.59, 9.6. Let's just say 9.6 degrees. 9.6 degrees, like that. This one's dark, and that occurs, that's n is equal to a half. Okay. Now, beyond that, we get another bright region like this. We found that to be 19.5 degrees. Okay. And that occurs at n equals 1. All right. What's next? Well, I didn't ask this, but if I said, well, next what? Well, the next one would be another dark region. Okay. And that would be n is equal to, that's a half. The next one would be 3 halves. Okay. Then the next bright region would be here. And that would be n is equal to, well, this one is n is equal to 1. This one is n is equal to 2. Okay, and so on. Okay, so I hope you can see the pattern. For the bright regions, it's 0 right there, 1, 2, and then straddling between those, okay, is a half, 3 halves. The next one over here would be, over here would be 5 halves, okay, and so on. Okay, so you can see that the dark regions are directly in between the light regions. All right, now I didn't do a problem with a single hole. There's a similar formula for the single hole, but I figured, since we did one with in detail for the double slit, that was probably good enough. Okay, now that if there's no questions, that's it for the non-calc part. Okay, so the rest of this, there's two more questions. They're not that long, but they're only for the calc students. Everything preceding was for both classes. The next one is just for the calc-based physics. Okay, so let's start that. All right, let's make sure there are no more questions. No, I just see some of the older questions. Okay, so all right, let's start. So danger, calculus ahead. All right. So in that second lecture that I gave, the Physics 102, we discussed this wave equation, and here it is. Here's the wave equation. Now that's writing it in the text editor, it's a little bit ugly, but basically y is the amplitude. Okay, so just remember from the lecture, y is the amplitude of the wave. Okay, and it's a function, actually. Maybe I should just write this somewhere. I don't know where y is a function of both position and time. Okay, because you get wave behavior in both position and in time, and I've got a diagram for that I'll show you in just a second. Okay, but you take that amplitude as a function of both position and time. If you take the second derivative with respect to time, you get you get a function, and similarly you can take the second derivative with respect to x and you get a function, and the two functions are going to be identical except for a constant, and that constant turns out to be the velocity at which the wave travels squared. Okay, so this is known as the wave equation. So the first question is, what is the physical interpretation of this thing? Okay, well, I just told you the physical interpretation of v squared, that's the velocity squared. But what's the physical interpretation of the second derivative with respect to time? Okay, and what's the interpretation of the second derivative with respect to x? Okay, and to answer that question, I'm going to just show you a diagram. Wrong one. Okay, and there it is. Here's our diagram. Okay, so what are you seeing here? The red line is basically a point on the wave here, like that. Okay, and if I asked you, what is this point doing in time? So what is the point doing in time? It's going to oscillate up and down in time. That's what it does in time. So the amplitude is, where should I write this? I mean, maybe the amplitude is like this. Okay, so the amplitude, if you take its second derivative with respect to time, that's the red. That describes the behavior of the wave. That describes the behavior of an oscillator at a particular point in space. Okay, so it's just the oscillator. And what does it do? It just bobs up and down. Okay, so there you go. That's what the second derivative with respect to time refers to. The motion of an oscillator in the wave moving up and down. What about the second derivative with respect to x? Well, x is this way. Let's do that in red too. X is this way. Okay. All right. And if you're talking about the second derivative with respect to x, that's the blue, because the second derivative with respect to x is how does the thing change over x, and so that's the wave structure or the waveform. Okay, so this piece describes the waveform. So there's a relationship between the waveform, the blue line, the shape of the wave, and the oscillation of any one particular oscillator. Okay, so this equation basically says, how do these single oscillators that are oscillating in place over time, how do they give rise to a waveform? And the answer to that question is this equation here. And as you can imagine, the two are related by a constant, which is the velocity. Okay, so in answer to the question, what does the second derivative with respect to time? That was the red line, and it's basically an oscillator motion in space. Okay, sorry, in time. I'm sorry, guys, in time. Okay, or over time. It's like, how does a single oscillator move over time? It oscillates. Okay. And what about the second derivative with respect to x? That was the waveform. That was the blue line. And it's basically the wave shape or waveform, like that. Okay, in space. All right, there you go. That's the physical interpretation of that. Okay, well, there wasn't much to ask there. I just wanted to, before I jumped in and did some math with it, I just wanted to clarify that. Okay, now what about a more substantive problem? Okay, so this problem kind of encapsulates everything that I could ask about this. Okay, and starting from that equation, okay, and given that this is a solution of this equation, all right, can you derive that v is equal to lambda f? And v is equal to lambda f is basically the equation that we use right back up here in equation number 1. It basically says, look, the velocity of a wave in some material is constant, okay, and it's related to lambda and f, but if you change lambda, you're going to change f correspondingly so that the v remains constant for that particular material. Okay, so down here, can we actually prove that out of this? And the answer is yes. Okay, so here's how you do it. So let me read the problem first. Starting from the wave equation, that, okay, and the solution, that y is equal to a cosine kx minus omega t, derive v is equal to lambda f. Also, what is going to be the relationship between k and lambda and omega and f? Okay, and that second part will come out as we do this. Okay, so let's take a look here. If you take this, all right, this is basically take this function here and differentiate it twice. Let me put that function in brackets here like that. Differentiate that function in square brackets. Let me move the cursor aside here. Differentiate that function in square brackets twice with respect to time. Well, the first time you differentiate it, you're going to get an omega in front, but then it'll become a sine. And then the second time you differentiate it, you're going to get another omega in front, and then it'll go back to the cosine. And you'll get an extra negative sign in addition to that. So you get the same function back, but you actually get the same function back with a minus omega squared in front. Okay? All right. So there you go. There's the second derivative with respect to time. Okay, and I did show that in the lecture, so I'm not going to go over the details here, but once again, the first time you differentiate that function, the cosine becomes a sine. The second time you differentiate it, the sine goes back to a cosine. Also, each time you're differentiating with respect to time, but there's the extra factor omega in front, and so you get a factor omega each time you differentiate, and that gives you an omega squared in front. And the negative sign comes from the fact that when you go from differentiate the cosine, you get negative sign, and so you get the negative sign in front. Okay, and then when you differentiate the sine, you just get a plain old cosine back. Okay, so that's the negative comes from one of the differentiations. Okay, enough said there. Okay, now what about differentiating it twice with respect to x? So if instead of t there you have x, well, what's the factor in front of the x? The factor in front of the x is k. So you don't get omega squared, you get k squared out in front. Okay, so there you go. There's the second derivative with respect to time of that function, second derivative with respect to x of that function. Now what? Well, if we go back to this equation here, okay, this is supposed to be a solution. So for this, the second derivative with respect to time, let's put that in there. Okay. All right, so you can see that was the second derivative with respect to time. There it is. Then there's the v squared. Okay, let's put that in round brackets like that. And then when we differentiate with respect to x twice, we get this. Okay, and we should put round brackets around that because we're multiplying. All right, so there you go. There's the wave equation with the solution plugged into it. Okay, now you'll notice on both sides that you have that a cosine kx minus omega t. Okay, well, that's got to be true for all t and all x's, so that'll cancel out. Okay, so on the next line, you simply get this. Okay, and again, the A cosine omega t, that was common to both sides, so it just factors out. Okay, well, there's a negative sign on both sides, and there's also a square there. Okay, so the next line, I can get rid of the negative sign, and I can get rid of the square. So let me just do that. The negative sign goes away because there's a negative sign on both sides. And we could take the square root of everything here like this. And we get this equation. Okay. So we can pause there a second because that looks an awful lot like this equation. Compare to that equation. Okay. So they look very similar, but they are actually the same equation. But this one is in terms of the angular frequency, omega, and k is called the wave number. Okay. Now, what's the relationship between omega and f and k and lambda? And the answer is this. If you go back to this form right here, we don't even need the a in front, which is just the amplitude. Notice that you have kx. Okay. Well, that has to make one complete oscillation in 2 pi. Okay, why? Because the cosine oscillates in 2 pi, so that's going to equal 2 pi there like that for one cycle. And I don't have a pi anywhere, do I? Let me grab a pi from my my word processor. I got to cut and paste the Greek letters from my word processor into my text editor. Okay, there we go, 2 pi for one cycle. But what's x for one cycle? What do we mean by x for one cycle? Well, take a look here. One cycle is from, well, let's do it in green, from there to there. I know it's a bit messy, but there it is. That's one cycle in x. So one cycle in x is also called lambda. Okay? So back over here. Yeah, it's x, but for one cycle, x has the name of lambda. And so lambda, or k, can be written as 2 pi over lambda. All right. Okay, so that's one of them. K is 2 pi over lambda. I asked what's the relationship between k and lambda, and the answer is k is 2 pi over lambda, because k times lambda must be one complete cycle, and one complete cycle of a cosine is 2 pi. Okay, what about the other one? Well, the other one now is going to be omega t. That has to be one complete cycle. But for one complete cycle, we get this. Omega t is equal to 2 pi for one complete cycle. But we have a special name for t for when you have a complete cycle. One complete cycle in time is the period. Okay? And so here's another one. You can write that omega is equal to 2 pi divided by capital T. But I didn't ask for the relationship between the angular frequency and the period. Okay, I asked for it between the angular frequency and the linear frequency. And just remember that the angular frequency, sorry, the linear frequency is the reciprocal of the period. And so you could write that this is equal to, remember 1 over t is the same as f, like that. Okay, so there's our second relationship. Okay, so now what? Well, we have this equation, which we just got out of the wave equation by differentiating. Instead of omega, let's write 2 pi f. Okay, so omega here is 2 pi f. V is just plain old v. Okay, so that was that. Omega is 2 pi f. V is still just v. And for k, I have 2 pi times lambda. There we go. Now what? Well, both sides have a 2 pi, so divide that out. Okay, 2 pi is gone, 2 pi is gone. Okay, now what? Multiply both sides by lambda, and we get that lambda times f is equal to v. And ta-da! We're back to the very first equation that we even started with. Okay, v is equal to lambda f. All right. Oh, down here I have it the other way around, but you got the idea. Okay, so v is equal to lambda f. All right. Where's that coming from? It's coming from this equation here. And why is that equation at all interesting? Because that equation basically ties the oscillation of individual oscillators to the waveform. Okay, and that's exactly what a wave is. All right, so there you go. That's pretty much all you need to know for that. So what kind of questions would I ask? Well, these kinds of questions, but I'd break them up into pieces. Okay, remember the test is multiple choice. So I would say, something like, okay, so this is a solution. What's the second derivative with respect to time? And you better be able to pick that one out. What's the second derivative with respect to x? So that one, okay. If you substitute this into this, what do you get? Well, you better know that equation comes out, okay. And what's the relationship between the wave number and lambda? Well, that's the relationship, okay. And I'm going to scroll that down a bit. So that's the relationship, okay. And what's the relationship between the angular frequency and the linear frequency? Well, there it is right there, okay. And then finally, you should know that this equation, when you switch from the angular quantities to their linear quantities, will give you that equation. Okay, so that's it. That's it for the calculus part. All right, let me see if there's any questions in the chat, and there doesn't seem to be. So that's it for our live stream this evening. Okay, and we've covered all of waves. All right.